This is my lab 3 on the black hole. The purpose of this lab, it has two parts. The purpose of part 1 is to find the mass of a black hole by analyzing the motion of a star. The purpose of part 2 is to use the calculated mass of the black hole to determine the initial velocity of a spaceship that will allow it to get close enough to the black hole without crashing or getting sucked in. Some important models and principles for this lab. Glow script was needed to complete this, as well as universal gravitation concept, Newton's second law of motion, the momentum principle, position update formula, and velocity update formula. Here's a preview of the result for part 1 and part 2, and I'll explain how we got to this. So the system and surroundings for at least the first part are the star and the black hole. And the initial conditions, the mass of the star is 2 times 10 raised to the 30. Change in time, delta t, is 1 day. However, for the sake of getting correct calculations and formulas and things, had to convert that to seconds. So 86,400 seconds in a day. And so that is the value that was used. And the time for the first observation is t equals 0. And the gravitational constant is 6.7 times 10 raised to the negative 11. For the procedure for finding the mass for part 1, put in first the mass for the star, 2 times 10 raised to the 30, and then inputted the time interval between the imported data points, like I said previously, the 86,400 second value. And then next in the section 2, in the calculation loop, had to edit the code formulas and all of that you see here to make sure that it's doing the correct steps to get the mass at the end. And then same thing in section 3, editing the code to draw arrows to represent forces. And so putting all of that together, those 3 parts together, then that gives you the mass. And so ultimately you have the mass of the black hole, 2.329 times 10 to the 34 kilograms. And then also this model and everything gives you the magnitude of the net force, the magnitude of the parallel component of the net force, and the perpendicular component of the net force as well. And so all of those are listed here. And so then taking this to part 2, first thing we do is input the mass of the black hole into this section 1. And then also we have to sort of guesstimate what the x and y values are going to be for initial velocity. And so just kind of like plugging in, guessing, and checking there to see what gets the model to run and what works and what gives you the best approximation. And then in the calculation loop, editing the code to get ultimately what you need with that initial velocity. And so all of that is shown in the red box there. And so the result, the initial velocity I found was negative 12.4 times 10 to the 6, 13.2 times 10 to the 6. And then the closest distance to the black hole is 3.741 times 10 raised to the 10. And so as far as possible error goes, at least in part 2, then approximation was used for the initial velocity. So it may not be 100% accurate. It was kind of like a guessing check, see what works, see what doesn't work until you get close enough. So it may not be exactly the accurate number, but it definitely is close and it works. And so also using a different time could affect the speed. And then for what does it mean? Net force requires you to know the black hole's mass, while the change in momentum allows you to solve for the mass relying on the position, velocity, and momentum of the star. And so in that sense, these values change over time. And so in summary, kind of changing a change in momentum, the change in momentum is easier to find than the net force. And then for the what if, I wasn't able to find the exact value, but the star or the ship must have a similar velocity to the planet. Your y will just need to be larger, and the x would have to be smaller. And that concludes this lab.